So it's a pleasure to have all of you here. So my job in the next few minutes is to kind of introduce the sort of overall topics of the course. I note that we have a rude gong that you heard to summon all of you to your seats. If I should run over time, which the students will get to gong me, and we will gong anybody else that runs over time as well. So you can look forward to the humor value of that. So my job is to kind of start things off and tell you a little bit about energy research and teaching. And actually, there's so much that I'm not going to try to do it all, but I'm just going to give you some hints. And then during the week, there'll be much more opportunity for you to hear about what's going on here. So energy is an absolutely essential component of modern societies. And so you can't contemplate living in a world that doesn't have the kind of lighting and transportation and computing and all the services that go with electricity. But it's also one of the primary ways we interact with the world around us. And it's quite clear now that we humans are a potent biogeochemical force acting at global scale. And we really need to do a much better job of understanding how we interact with the natural systems and paying attention to that as we design the energy systems of the future. I think it's, for most people on the planet, we take all those natural systems completely for granted. But we shouldn't do that, and it's time to do a better job. And the truth is, that's your job. We're going to help try to give you the background needed to do that, and we'll try to engage all of us in the kind of research that's needed to support the transitions in energy services that are going to have to happen in this century. So the challenge is, I have to say, a huge one. We have almost actually 7 billion people on the planet now, and the current projections are that we will get to 9.5 or thereabouts in this century. So just providing food and fresh water and energy for all those people is already a pretty daunting challenge. We need to do that much better than we do now, and of course as the standards of living improve in some parts of the world, those people have every right to expect to be able to use energy services that all of us also take for granted. So that's a big challenge, but we also need to think about how we're going to maintain the planet in a habitable form. So I think that means we now are in an energy transition. It's underway now, and although it's at the beginning, but it's not the first one. This slide is in percentage terms, so it's a little misleading. I'll come to that in a minute. But we started, this is US, but the world was really quite similar. So in the 1850s, wood provided most of the energy. Then coal came in. That's this big gray streak, and we had a transition to coal. And then there was a transition to using oil. The coal didn't go away, of course, but oil was used, and much of it, of course, is now used for transportation. Natural gas appeared later, and here's the nuclear side. And if your eyes are really good, you might be able to see the little slice of renewables up there. But remember that all these other things started with a little slice, right? So that's a goal. But one thing that is obvious from this is that you don't do these kinds of transitions overnight. They take decades, especially given the size of the energy system now. We have lots and lots and lots of infrastructure that is going to change over time as we do this. Now, this is another version of this. So this just makes the point that percentages don't tell the whole story, because even as, so for example, if you look at coal here, even as the fraction of coal in the energy mix went down, the total amount of coal use continued to rise, except for this last year. It turns out that if you have a global recession, demand for all kinds of energy services goes down. That might not be the best way to manage reducing emissions, but in any case, it does work. And so you can see the use of petroleum skyrocketed over time as we figured out that we could drive ourselves around and fly in airplanes and use it on ships. But so energy use grew a lot in the time that all those percentages were changing. And it's the size of the system now that actually makes it a tough one to change. Now, these things have economic consequences. So the energy system, it might be designed by a bunch of engineers and scientists, but it's run by a system of businesses, and all of us make choices about how we use energy and what the costs are. One price that seems to be on everyone's mind is the price of gasoline. And so this is the price of oil since the 1860s. And you can see that there have certainly been times where there's been lots of volatility. Most of you aren't old enough to remember the energy crises of the 1970s, but I certainly do. And then we've had a period of instability here. In both of these times, these were times where the overhang of supply as opposed to demand, they were pretty close together. So any bits of fluctuation or politics or wars or those kinds of things really did influence the price on a short-term basis. But in the end, supply and demand operate. So we do have to think about how to make these the energy systems we put in place work in a set of markets. So that will be part of what we talk about this week. But there's also something that's really pretty different from the energy crises of the 1970s. Then we were worried about how do we have enough fuel for our vehicles. Now, of course, we've realized that much of the carbon we've burned over the last century has stayed in the atmosphere, and that has leads to climate change, potential for climate change, for dissolution of CO2 in the ocean, and a whole series of challenges that we also have to find a way to deal with. And takes good eyes, I think, but you can see here that the carbon dioxide concentration in the atmosphere has gone from the ice age values in the 200s up now it's about 390 parts per million, so that's increased by a third. The methane concentration has more than doubled, and the nitrous oxide concentration is increased as well. So we have modified the planet on a global scale. One area that's gotten less attention, but I think is also very important, is the pH of the ocean. So all that CO2 that we put in the atmosphere, that's busy dissolving in the ocean at some rate. We kind of keep it in the atmosphere for a couple of hundred years first. But when it does, it lowers the pH. And when you change the pH, that changes the concentration of carbonate and bicarbonate ions. Those are ions that all the little critters in the ocean that fix calcium carbonate make use of those. And so, and those little guys are at the base of the food chain. So everybody in the ocean eats them or eats somebody who eats them. And so population balances in the ocean are certain to change. So that's an experiment in a way like climate change. That's an experiment that we don't understand very well looking forward what the outcome is going to be. So even if you didn't buy any of the climate change stuff, we need to be thinking about how to deal with that. So you say, well, of course, okay, we all agree. It's we should get to work on that, but the prognosis is not great for the moment. You can see the total energy use, and the slots here are the gray is coal, the little orange bit is renewables, this is hydro, the yellow is nuclear, natural gas, and oil. And so you can see that despite the worldwide recession here, energy use and mostly fossil fuels has continued to grow. So we have also seen that carbon dioxide emissions have continued to grow. So if you look at greenhouse gases and how they function, they're not exclusively energy, but they're about, at least for US, it's about 80% energy, and the rest of the world is not hugely different from that. So the energy-related CO2 is this part of the circle. Methane is here. Nitrous oxide is here. Other high global warming potential gases are here, and other CO2 is down here. So of the fossil fuel related side, it's petroleum, coal, and natural gas. And if you look at the direct use of fossil fuels in heating homes, it's kind of a third of electric power, transportation, and direct use in buildings. So if you think about what the opportunities are to do something, they really fall in these three broad categories. Electric power generation, very important. It's done at the moment now centrally in big facilities. Buildings are a big opportunity because all of us make decisions about how we use energy in buildings. So we'll talk some more about that later on this week. And then transportation is another big area where there are many opportunities. I think it's clear now that we could, if we really implemented a deep set of penetration into the markets of more efficient vehicles, we could have a significant impact on that. So as I said, the news isn't terribly good on the carbon emissions side. This plot is, for those of you that might be familiar with the IPCC, the Intergovernmental Panel on Climate Change, they've done a series of assessments of climate change and its impact. And they did a whole series of scenarios in which they looked at various different how the future might develop. And one message from all of that is that it really does matter what we do in this century. So that's both good news and bad news. The good news is that we can influence what happens, and the bad news is so far we're not doing it. But you can see that the actual carbon emissions, these black dots, are kind of at the high end of the range of the various models, except for the emissions reduction in the recession in the last couple of years. So these are projected numbers up here. But we have a lot to do. We have a big challenge, and we need to get to work on it. And just so you have some sense of what happens to all that CO2, it goes into the atmosphere. Some of it's taken up by plants. Some of it dissolves in the ocean. But the net result is that we've been adding CO2 to the atmosphere at about, say, 1.5 to 2 parts per million per year. Okay, so we're at 390 now. And if we keep doing that, we'll pretty quickly get to the 450 parts per million that seems to be a sort of generally accepted number for trying to keep climate change within a couple of degrees Celsius. So big challenge, and something that we really do have to face as a society. Energy, of course, is deeply connected to world trade. This plot shows various emissions rates in million tons per year associated with various kinds of trade activities. A fair amount of this is energy trade, but there's, for example, a lot of manufacturing now is in China, and so those big arrows are the emissions associated with manufacturing in those places. The United States does some manufacturing and selling to Europe, for example, too. So it just gives you an idea that this is all connected, and it's connected through the complexities of the international trade system and the way all these economies work. So if you think about it, energy is involved in environmental interactions, in economic interactions, and to some extent in international security, because we certainly at times have disputed over access to oil and access to energy. So what happens to the energy? This is the picture for the United States. Here are primary energy resources over here. There's the sun up there, nuclear and so on, natural gas, coal, and petroleum. And so those flow into various uses. So for example, coal generates about half the electricity in the United States, and natural gas is a lot of the other parts. And then oil goes largely into transportation. But the interesting thing is that the thermodynamics mean that not all the energy that starts out in the primary energy resource ends up as an energy service. There's some price that has to be paid thermodynamically for each one of those. So if you have an old, relatively low temperature, low pressure steam turbine driven by a coal-fired power plant, the efficiency is about 34% on a good day. So that means about 2/3 of the energy that was in that coal ends up going out the cooling tower or up the smokestack. So you say, well, gee, we ought to try to do better than that. If you do it now in a relatively new natural gas combined cycle plant, then the efficiencies can be in the 50 to 60% range. We actually have here on campus a combined cycle gas turbine plant, and it's actually nearing the end of its life, but it's in the kind of 50% range. So that's definitely better. And if you remember that methane has less carbon per unit energy in the fuel than coal does by a fair amount, and that's actually does better on the CO2 side. What this means is that every time we transform energy from one form to another, so you start with some primary resource, might be the sun, and transform it into something else. The solar cells that I have at my house are about 17% efficient, so 17% of the sunlight ends up being electricity. So we can, if we're trying to reduce carbon emissions, then we can reduce the carbon in the fuel or eliminate it. We can make the transformations more efficient. The transformations, I mean something like converting to electricity or to mechanical work in a vehicle. Or we can have fewer of the changes in form. Every morning when I make my piece of toast in my toaster, I think about the fact that we paid a big thermodynamic penalty to make the electricity that went in my toaster, using it as heat. And then, of course, I turned it right back into heat to make my toast. It seems like an inefficient way to do it. On the other hand, I don't really want to have to build a fire in order to put my toast over it. So it provides a service that really has a value in the right size and the right place. So those are the kind of balancing things we have to do. So how do we change all this? Well, first we should look for energy efficiency at every opportunity. There's a huge area of low-hanging fruit that we could do a lot. We're going to need to work to mitigate the impacts that are already in place. We need to find some way to charge ourselves for greenhouse gas emissions as a way to make ourselves pay attention. But for all of us here in the university, we need to work on a spectrum of energy resources and conversions and timescales, and build a full and rich portfolio of effort across the energy spectrum, and that's what we're trying to do. Now, the good news is that there's plenty of energy out there. It's all about conversions. And you'll probably see this slide multiple times during the week, so I'm not going to explain it all. But this gives you some sense of the energy landscape, that is the resources that we can convert. And these flows are in terawatts, for example, and we humans use about 15 terawatts now. So there's lots of energy out there, but what we need to do is to convert it in an economical way, and so we'll talk about that this week in a lot. And there's a lot going on here at Stanford. You'll hear from people involved in many of these efforts as the week wears on, and all of these departments and programs have some teaching and research. I have a little table of all the acronyms, which is at the end of this presentation. We'll make sure you have it, and that will allow you to deal with the alphabet soup here, I hope. So ZX mentioned that I'm the director of the Precourt Institute for Energy. This is a relatively new organization that is intended to try to bring all of us together in a way that makes us a more productive and more capable group of folks. And so we're looking forward to adding all of you to that mix. Among other things, we have a weekly energy seminar, and you're welcome to join us. It's Monday afternoons at 4:15, and Sally Benson and Lee Johnson and others have put together a tremendous program for the year. And so please join us. We routinely have 100 to 200 folks who show up for these, and you can get just some idea of the themes coming up: solar energy, underground storage of various things, and then a kind of a saving the world and having a job sequence of things. I think that given the magnitude of the challenge, there's plenty of opportunity for jobs. So I think you're in a good field if you're. And of course, you know, we're doing the Energy at Stanford and SLAT course this week, and looking forward to your participation in all of that. We also, of course, are working here on the campus as a place where we live and work, and trying to make the campus much more efficient, and so you'll get a chance to hear something about that. So, Ziek said this, we want to provide a wide-ranging overview. We want to introduce some of us that are involved in the research, and in particular, we want you to meet each other, because we know that good things will flow amongst the many conversations that will happen over time. And the real goal is to build as vital and vibrant an energy research community as we can in this place. Stanford is a place that brings together a lot of talented people, and we know that this is an area that really needs your talents. So we have, you have the schedule, I know, so I won't say anything about that, and I won't even try to explain the energy spectrum here. You'll just get a chance to do it. So here's the list of goodies, of acronyms, and we'll provide that as well. And here's the list of departments and programs that do research, and another list of ones that do some sort of teaching activities. And so with that, I will stop.